So here is the quadratic formula. Most of you have encountered this before, but did you know where it comes from? Well, first a little history. It was formulated over, the problem, at least, was formulated around 2000 BC as far as we have records of people needing buildings of different shapes and sizes, particularly area. And so if you have the area of something, and then of course those shapes got a lot more intricate and varied, and the question was, well, what if I want a certain area, then what kind of shapes and sizes should my floor plan be? And so around 1500, we see, this is all before Christ, in Egypt, basically engineers came up with tables, kind of like we have times tables today, where you have all sorts of solutions that they're looking for in terms of these different problems, and then you would just look up what different possibilities existed, and you could choose what fit your situation until about 400 BC in parallel in Babylon and in China. People independently came up with a process that was pretty close to what we learned in a previous video as completing the square. At that point, we didn't have a firm grasp of, well, at least, how to calculate a square root. I mean, I can't even do that by hand. I need a calculator for this if it's not a perfect square. So without that, they could get close. And the powerful thing was that they could really check their work, the engineers in Babylon and China. In Babylon, because their base 60 system allowed for much faster calculations, and then in China, the abacus allowed people to double check those solutions and to make sure that those worked. And so the rudimentary versions of completing the square were around in both of these areas in 400. Then by 300 you have the Greeks and Euclid and the beginning of an understanding of irrational numbers. And so jump ahead to 700 AD, as far as we know, the Hindus were the first ones that we know of to actually have included the irrational numbers that were needed to basically solve a quadratic for all numbers. But sort of for millennia, it's kind of this hunt for a general formula for the roots of some sort of square equation. So, with that background, here it is. So, our quadratic can be generalized with these three variables a, b, c as the coefficients of x squared, of x, and then a constant. So if we set it into the form with 0 on one side, then we have these three constants. And a needs to be non-zero, otherwise it's not a second degree, it's not a quadratic equation, and therefore this does not, doesn't fit this situation. But b and c can be 0. But anyway, we've got these three coefficients, a, b, and c, and those are the variables that you see in this formula as solutions, the two solutions for x, right, because of that plus or minus, up to 2. We'll talk about that. Alright, so where does this come from? Well, it really does come from completing the square on this generalized formula. Generalized because, therefore, it will work for any formula. well, any quadratic formula, that is. So, if you saw the videos where we actually worked with real numbers, sometimes I like to do that side by side, a generalized on one side and then with numbers on the other. But for the sake of length of video and time, today I'll just focus on this, and if you want to see it in action with numbers, I would go and look at the video completing the square 2 and watch these in sequence. Alright, so as with the last the video with numbers, this first step is sort of optional. I like to throw the constant over on the other side just to clear the space over here. You don't have to. The next step, which is quite necessary, is to divide both sides by a. It just makes everything a whole lot easier. And so now I've got x squared plus b over ax equals negative c over a. Okay, and now for a little bit of logical thinking. If this, just looking at the left side, ignoring the right member, looking at the left side, the idea in completing the square is to turn this into a perfect square, the square of a single binomial. Alright, so since I've divided out a, that makes the x term easy to figure out, and again these two are going to be the same, so that I'm going to write it here, right, so it is the square of a single binomial. Alright, now we also know what has to go here, because when I multiply this out, and I'll put that down here, I am going to get x squared, I'm going to get this number times x plus this number times x, and since these two terms in parentheses are the same, I basically have this times x plus this times x. My result is going to be twice whatever this single product is. And at the end of the day, what I need that to add up to is this, b over ax. And so what I need is a half of b over a for each of these spots. B over a times a half, or b over 2a. B over 2a. Alright, now let's see what happens when I multiply that, just to show ourselves that this is in fact the case. Alright, so I got x squared plus b over 2ax plus b over 2ax. Alright, I'm going to leave aside, well, let's go ahead and multiply that out. We have b over 2a squared, which is b squared over 4a squared. Okay, so that's me just multiplying this out. And I'll go ahead and fill this in here. Okay. Alright, so this is my perfect square that I'm going for. And now let's make sure that this, in fact, does add up to this, because I need to represent what I have here accurately. Well, b over 2a plus another b over 2a is 2b over 2a times x plus b squared over 4a squared. Those 2's can cancel out, and indeed I have b over ax. Alright, so this squared will indeed give me this as my coefficient of x and x squared. Now, you notice once we did multiply that, it also gives me this constant. Oh, well, in completing the square, that's what I get to add to both sides in order to complete the square. Ah, so this is the number that I need to add. So, plus b squared over 4a squared, and I add that to both sides, b squared over 4a squared. Okay, so that's the term I'm adding to both sides to complete the square. And what the square is this, right over here, this line here. So let's go ahead and work with this line, b squared over 4a squared. Okay, so now I can use the square root property, take the square root of both of these, and let's come down here. Okay, we'll ignore the stuff in between, that was just me verifying things. Over on this side, the square root will give me now x plus b over 2a. It doesn't need it to be in parentheses. And then over on this side, we'll do a little rearranging. I'll put this, just swap places. So this is b squared over 4a squared minus c over a. And next, let's combine this into a single fraction. So common denominator would be to multiply by 4a over 4a. That'll give me 4a squared on the bottom of both of those. So x plus b over 2a is equal to, and I've got my plus or minus here on my square root, plus or minus the square root of b squared minus, we'll just rearrange these 4ac, already seeing the quadratic formula emerge over, all over 4a squared. Alright, now go ahead and subtract b over 2a from both sides. And now I've got x equals negative b over 2a plus or minus. Okay, and then you remember for a square root of a quotient, that's equivalent to the square root of the numerator over the square root of the denominator. Which is nice because this is a perfect square, right, of 2a. Oh, look at that. And so then I have x is equal to negative b plus minus the square root of b squared minus 4ac. And 2a here, this is also 2a, I can combine that. All of that is over 2a. And that is indeed the quadratic formula. Now I want to draw your attention to one particular thing, since we're looking at the formula right here, which is this. This is the discriminant. Discriminant y. It helps us discriminate between three particular situations. Okay, number one. Let me write this out again. I've got two solutions for x here, and this is the compact version of the formula. But my two solutions would be, right, there's the one, and there is the other. Just to be clear, those are my two solutions for x. Now, situation number one is if b squared minus 4ac is less than 0. Or you could also see that as 4ac being greater than b squared, right? Taking something greater from something that's smaller than it, I will end up with a negative. That causes this to be the square root of a negative number, which is going to be an imaginary number. Imaginary. And so, if you're looking for real solutions, then in this situation, you know there are no real solutions. For a parabola, this is where there are no zeros or places where it intersects the x-axis, if you already have a background in connecting these with their graphs. Alright? So, no real solutions. No real solutions. Imaginary ones, yes, but no real ones. Alright, my other situation. What if b squared minus 4ac equals 0? Well, in that case, this becomes negative b plus or minus 0. Oh, well, that's negative b minus 0, which is just negative b, and negative b plus 0, which is just negative b. Oh, these two become the same. Oh, in that case, this has one real solution. and we'll talk about why this is interesting. So that's if b squared is equal to 4ac, right? The difference is 0. Or if b squared is bigger than 4ac, then b squared minus 4ac is greater than 0, then I have a value here. And then my solutions are going to be minus b minus something and minus b plus something. And since that is actually something, a non-zero something, I then have two solutions. So this is the two real solution scenario. Why is this a shortcut? Well, because before you do all this, whether you complete the square or use the quadratic formula, you can look at your quadratic as long as it's 0 on this side, because that's what this form needs to, what this form assumes is that one side is 0, and therefore whatever is left here is c, that's b, that's a. You can simply check. Take b, square it, and either compare it to 4ac or subtract 4ac from it. Right? So you can do that before you even try to solve it, try to factor it, try to do anything. You can check, does it have solutions? Does it have any solutions, real ones? Does it have one? Does it have two? Etc., etc. So you can kind of scout it out just by doing a couple quick multiplications before you try to factor, complete the square, use the formula, solve, etc., etc. See if it's even solvable in terms of real solutions. Okay, the other thing that is very interesting that we'll go into in another video is, right, so this is the no solution graph. This is a two solution graph, right, so it's got 2 points. And this is the one solution graph. The one solution happens to be the minimum of that graph, or if you have an upside down parabola, and you're looking for, is it equal to something? Right, that one solution, or you could have it over here, that one solution is the maximum. And so there are all sorts of situations, whether it is the height of an object, a projectile, or a profit curve for a business where you're looking for a maximum, or maybe a cost curve for a business, you're looking for the minimum. And being able to identify this, where you can tweak A, B, and C, is really valuable, practically speaking. So that is the value of the discriminant. Not just to figure out whether or not a quadratic has solutions, but you can also look for specific situations, such as the minimum or maximum of a curve.